Hey there. In this video, we're going to do a couple of Laplace transforms where there's a translation going on. And normally we see a translation when we're taking the Laplace of a function times e to a times t in general, where a is some number. So my first example, we're going to apply the Laplace transform to t cubed times e to the 5t. So I have a product of two functions. The e to the 5t tells me that I can use a translation formula to apply that Laplace function. And I have my translation formulas up in the top right corner to kind of help me out with this. These are not worth memorizing. They're great just to have handy when you need to use them. Okay, so I want to take the Laplace of t cubed e to the 5t. And another way of thinking about this is a translation of t cubed, where s is being translated to s minus 5. Okay, and so that kind of takes care of that e to the 5t. There's my translation. So now I can just use a standard t cubed Laplace transform formula, and then just wherever there's an s, I replace it with s minus 5. And that's essentially what the formula on the right does as well. So here, t cubed would be 3 factorial over s to the 4th. And so that s to the 4th is just going to become s minus 5 to the 4th. And I can simplify that just by evaluating the factorial. So 3 factorial is 3 times 2 times 1, which is 6 over s minus 5 to the 4th. All right, so that's how I can do a Laplace transform using a translation. Now let's do an inverse Laplace transform being applied to a function. So here I have a function of s, 2s plus 5 over s squared plus 6s plus 34. And I want to be able to apply a Laplace inverse to this. And I can use my formulas over here. Just know that I'm working from the right to the left now on these formulas. So this one kind of reminds me of my cosine and sine functions, but it does look a lot different in its current form. So the first thing I'm going to do is a little bit of side work. I want to first deal with that denominator. So I have a quadratic here, s squared plus 6s plus 34. If it was factorable, I could do a partial fraction decomposition and break this fraction up, and then maybe I wouldn't have a translation anymore at that case. But this one's not factorable, the denominator. So instead, I'm going to use completing the square to change the denominator to look more like the s minus a squared plus k squared that I have in my Laplace formulas to the right there. Okay, so looking at s squared plus 6s plus 34, completing the square is something you should have learned in like an algebra or pre-calculus course that just kind of comes up at random times as a useful thing to do. And how that works is I'm going to take this constant for the middle term, the s term. I'm going to divide it by 2. So 6 divided by 2. And then I square that value. So this is going to be 3 squared, which is 9. And what that number tells me is what I need the constant term to be in order for this to be a perfect square trinomial that factors into something like s minus a squared. So here I need a 9 and I have a 34. So let's break up that 34. And so this is going to be s squared plus 6s plus 9 plus 25, because 9 plus 25 gets me back to the 34 that I started with. Okay, so now these first 3 terms are a perfect square trinomial that factors into s plus 3 squared. So I can rewrite my denominator as s plus 3 squared plus 25. So I'm going to go ahead and throw this inside the Laplace inverse, just to remind myself that that is my ultimate goal. And I have 2s plus 5 over s plus 3 squared plus 25. Okay, so this is looking better, but now the numerator doesn't look quite right. I have an s plus 3 being squared in the denominator, so I need an s plus 3 in the numerator as well to make this work. So what I'm going to do is actually I'm going to play around here on the side with some scratch work again. So I want an s plus 3 in there. And right now I have a 2 multiplying by it. So let's say I replace the s with s plus 3. So now I have 2 times the quantity s plus 3, and then I still have the plus 5 on the outside. Now I've added a 3 to this, which actually, because it's multiplying by 2, I've actually added 6. And so I don't have 6 here. I can subtract 1, though. All right. If I've added 6 here, if I subtract a 6 here, then I still have something that's equal to what I started with. Okay, so this is still equal to the 2s plus 5 that I had initially, if I were to distribute that all out. And so that's going to simplify to 2 times s plus 3 minus 1. And so that is what I'm going to rewrite the numerator as. So it looks kind of crazy that that's equal, but I am just rewriting it. It is equivalent to what I started with. So this becomes the Laplace inverse of 2 times s plus 3 minus 1 over s plus 3 squared plus 25. Okay, so we're getting a little bit closer to what the formulas look like. That minus 1 kind of throws us for a loop. The 2 throws us for a loop. Those two things don't quite match with the formulas. But I can break this up into 2 separate fractions, one with a numerator of 2 times s plus 3 over the denominator, and another one with the minus 1 over the denominator. So I'm going to do that. So now I have 2 times s plus 3 over s plus 3 squared plus 25 in one Laplace inverse, and then minus Laplace inverse of 1 over s plus 3 squared plus 25. Now things are really starting to look good. Now the first one, it has an extra 2 out front, but I can pull that in front of the whole Laplace inverse, and it's not going to be a problem. And so that first one is now looking a lot like the e to the at times cosine kt formula. And the second one is looking a whole lot like the one with a sine function in it. Okay, so for the first one, the only thing I need to do to make it exactly like it is pull the 2 out. So I have 2 times the Laplace inverse of s plus 3 over s plus 3 squared plus 25. On this second one, I need k in the numerator. And I have a 25 down below here, which is 5 squared, which means I need a 5 inside the numerator. So I need this to be 5 over s plus 3 squared plus 25. And I can do that as long as I undo it, much like I added 6 to my numerator and then subtracted 6. Here, if I multiply by 5, I need to also multiply by 1/5, and I'll pull that out front of the Laplace inverse. So it's still equivalent to what I started with if I simplified it, but now it's in a form where I can use my formulas. Okay, so we're now ready to evaluate both of these Laplace inverse. So the first one is going to be 2 times e to the at, where a is going to be negative 3, since the formula is s minus a, and I have s plus 3. That's like saying s minus negative 3. So e to the negative 3t times cosine of kt, and k here is 5. So that first one gives me 2e to the negative 3t times cosine 5t minus 1/5 e to the negative 3t times sine of 5t. And that is how you can deal with an irreducible quadratic in the denominator, and you're trying to do a Laplace inverse.